Section 6.1, multiplying and dividing rational expressions. Products of rational expressions are found by multiplying the numerators together, so a times c, and multiplying the denominators. And this should look very similar to how we multiply fractions together. Similarly, dividing rational expressions, if we have a division, we leave the first fraction or rational number as is. We invert the second fraction, which means we're taking the reciprocal of it, and do our multiplication. From there, then we would multiply the numerators together and multiply the denominators, and canceling out anything common in terms of factors to simplify the rational expression. So let's take a look at this first problem here. They're asking us to multiply a rational number by a rational number. Before we multiply, instead, let's factor and see what components are in each of these rational expressions. So on the first rational expression in the numerator, between those two terms of this binomial, we have a common 2. Factoring out the 2, dividing each term by 2, leaves us with a p minus 1 over a common denominator of 2. The second rational expression has a 3p to the second power. There's nothing we can do there. But in the denominator, we do have a common factor of 9, which we will factor out, leaving a p minus 1. So now we're ready to multiply our numerators together, multiply our denominators together, as is the procedure for multiplying rational expressions together. And we'll look in the numerator and the denominator for common factors that are equivalent to 1. We have a 2 over 2, or a 2 divided by 2, which is 1. We have a common binomial of p minus 1 over p minus 1 that cancels out. 3 and 9 share a common factor of 3. 3 divided by 3 is 1. 9 divided by 3 is 3. Or if you just reduce 1/9, you end up with 1/3. And that looks to be just about all that's common. Neatness definitely counts. We're left with a 1 times 1 times 1 times p squared. It's easy if you get a little sloppy to lose a factor along the line. And in the denominator, we're left with a 3. In this next example, we have a rational expression times a rational expression. And instead of taking a trinomial times a trinomial in the numerator and in the denominator and then trying to simplify, instead, let's factor each of these trinomials and see if we can reduce before doing the multiplication. So in the numerator, we're looking for two binomials that multiply to give us this expression. Both signs are the same on our 3. They're both negative. We only have one choice of 3 and 1. And if you check your outside inside, this is an equivalent expression. In the denominator, our x squared came from first terms in our binomials being x. We're looking for factors of 20, both signs the same, both negative, that add up to be 20. And if you go through your options, it ends up a negative 10 and a negative 2 do give us a negative 20 and do add up to be the negative 12. Times the numerator here in our second rational expression would factor into two binomials with the first terms being x. Factors of 90, both of them being positive, or both of them being the same sign and both being negative, that add up to be 19, are negative 10 and negative 9. Do your FOIL method to verify that. And in the denominator, we're looking for factors of 9, both signs the same, both negative. When multiplied, gives us a negative 10, which, when added, are a negative 9 and a negative 1. A FOIL verifies that this does multiply together and give us an equivalent expression. Now we're ready to multiply our numerator values together. We have 4 binomials, and in the denominator we have 4 binomials multiplied together. If there is something common, now is when we would cancel that out. Order is not important. Multiplication is commutative, so we don't have to have the same expression right directly above the value before we cancel it out. It just simply has to be in the numerator and the denominator. And if we look, we have an x minus 10 factor in the numerator and 1 in the denominator. Anytime you have the same thing over the same thing, it's equivalent to a 1. Inspecting this further, we also have an x minus 1 over an x minus 1, which cancels out, giving us a value of 1. We also have an x minus 9 over an x minus 9, which is equivalent to 1, leaving us with the binomial of x minus 3 over x minus 2. The canceling only occurs when things are multiplied together or are factors. So you need to be sure that your canceling is only removing out factors equal to 1. And when they are a sum or a difference, they cannot be canceled. So this is our final answer here for this problem. In this next example, we have division. But again, before we tackle the division, let's factor as we go. Common factor here is a 6 in the numerator. Dividing by 6 leaves a p minus 1 over p. The rule for division is invert and multiply, so our division turns into multiplication. The denominator comes up to be the numerator, and as we write our denominator, let's factor it as well. The 7p minus 7 goes to the denominator, but also factoring, greatest common factor is 7, leaves a 7 times p minus 1. Now we're at the same stage as we were with the last problems. We have two fractions or rational expressions that we're multiplying together. We'll look to see if there's something common in the numerator and the denominator and cancel. We do have a common binomial of p minus 1, which is equivalent to 1. We also have common variable p. P to the first in the denominator will reduce the number or exponential power in the numerator variable, leaving us with p to the first power. Number-wise, 6 and 9 have nothing in common with 7, so simplifying this, we have 6 times 9 times p, or 54p. In the denominator, we're left with a 7 for our final answer of this division of rational expressions. In this next example, it also is a division, and same procedure as the last one. Let's factor as we go along. In the numerator, we're looking for two binomials that multiply to give us this trinomial. Our first terms will be x. We're looking for factors of 60, both signs the same, both minus, that add up to be 16. A negative 10 and a negative 6 does the trick over the denominator of x minus 10. A division means we're going to invert and multiply, and this binomial is understood to have a denominator of 1, so our division becomes a multiplication, our denominator goes up, and our numerator goes down, and no factoring required. Now we're ready to multiply, but before we multiply our factors in the numerator and in the denominator, and I am putting parentheses around this to show that this is a quantity, we'll look and see if there's anything common to the numerator and the denominator. Well, we have an x minus 10 over x minus 10. They cancel out, leaving 1. Furthermore, we have an x minus 6 over an x minus 6, which is also equal to 1. We have a series of 1s in the numerator, which is equal to 1. We have 1s in the denominator, leaving us with 1 over 1, or a 1 for our simplified answer.